In video two, welcome to video two. So in video two, we have the formal definition of the vertical asymptote in connection with limit statements. And so what we're seeing in the box is the idea that if I look at a function and I take the limit of a function as x approaches some value from the left, and my answer is either positive or negative infinity, or if I take the limit of a function as x approaches some number from the right side, and my answer is positive or negative infinity, then there has to exist a vertical asymptote at that x value that we're approaching, right? So some things to remember, and I remember doing this in pre-cal, which is we can identify where the vertical asymptotes if once we simplify the rational function, whatever makes the denominator equal to zero, that will be a vertical asymptote. Remember that if something cancels out, what we learned with the indeterminate form is that if we have a factor and they reduce out, then that's a hole in the graph. That's a point discontinuity. That's a removable discontinuity. But if whatever's left over and doesn't get canceled out, doesn't reduce out, and whatever makes the bottom equal to zero, that would be the vertical asymptote. So for example, can we find all the vertical asymptotes of this function here, letter A, without looking at the graph? Now, if you want, after we do this, you can take out your calculator and your phone with the calculator, and you can verify that this is true, but can we factor the numerator? Is x squared plus 1 factorable? The answer is no. However, is x squared minus 1 factorable? The answer is yes, because it's a difference of squares. So then you ask yourself, if nothing reduces, and this does not reduce, if nothing reduces, then what x values would make the denominator equal to 0? Well, what x value could I substitute here that'll make that first factor equal to 0? If x equals what? 1. And then what x value would make this factor equal to 0? If x equals negative 1. So what we now know is, even though I don't know what the graph looks like, I do know that at x equals 1 and at x equals negative 1, there are vertical asymptotes. There are things going within the sections, but there are definitely vertical asymptotes, and therefore there's infinite behavior going on at those places. All right. What about letter B? Is the denominator factorable? Can I factor the denominator? Yes. I can factor that into x minus 2 and x plus 2. Can I factor the numerator? Yes. I can factor that into x, plus 4 and x minus 2. Yes. Can I reduce anything? I can. These are going to reduce. And what that means is that there is a hole in the graph, a point discontinuity, a removable discontinuity. I'm saying all the names of the same thing in the graph at x equals 2. So then what's left over in the denominator, whatever makes that equal to 0, whatever I just boxed in orange, whatever x value I can substitute in for x and makes that equal to 0, that's where the vertical asymptote is. And there is a vertical asymptote at negative 2. So the idea here is we know when vertical asymptotes occur. So therefore, how can I use that to help me with, evaluating some limits? Let's do a couple of these. We're not going to do them all, but let's do a couple of these. I'm actually going to do example 4 first. Can we find the limits? So what do we do whenever we're finding limits? Well, we apply the limit rules. The limit rules say, hey, substitute and do direct substitution into the numerator and into the denominator based on the x value that we're getting closer and closer to. So what happens when we substitute the 2 into the denominator? And some people would say, well, wait, we're approaching 2 from the right. That's okay. We're getting closer to 2, so 2 is the number we're going to substitute. 2 minus 2 is going to give me 0. And if I substitute 2 into the numerator, that's going to give me negative 3. So I now have a number divided by 0. When I say a number, I should say a number not equal to 0 divided by 0, because if it wasn't a 0 over 0, that'd be an indeterminate, and we know what to do. But this would be negative 3 over 0. Whenever you see that, that means there's infinite behavior. There is a vertical asymptote at x equals 2. But I want to know what happens, which way is it going? Vertical asymptote means there's an infinite behavior, but is it positive infinite behavior or negative infinite behavior? So what we do is we test a point. So I'm approaching 2 from the right. And if I approach 2 from the right, pick a point. I'm going to let x equal 2.1, right? And what I get, I'm not worried about what the answer is. I'm worried about what the sign, because this already tells me there's infinite behavior. I already know that the answer is going to be either positive or negative infinity coming from the right side of 2, or right side of 2. But I need to know whether it's positive or negative. So I pick a point to the right of 2, like 2.1, and I substitute it into my setup. So 2.1 minus 5 over 2.1 minus 2. Try to get the point as close as possible. You could pick 2.01, 2.001. The closer the better, right? But I'm going to try 2.1 just to kind of get us the idea. And the idea here is 2.1 minus 5 is going to produce a negative, and 2.1 minus 2 is going to produce a positive, and a negative divided by a positive is a negative. That means, maybe I'll write it out, equals a negative. And what that means is on the right side of 2 for this function, we are approaching negative infinity. Again, we already knew that there was infinite behavior. How do we know that? Because we have a number divided by 0. But now I know what type of infinity is on the right side. As it gets closer and closer to 2, it's going to go down because I picked a point to the right side of 2. I checked it and I looked at the sign. I really don't care what the answer is. I just care about what the sign to see if it's a positive or a negative infinity. We'll do some more examples here in video 3.